Chapter 1 is on matrices and Gaussian elimination. This is from linear algebra and its applications. By Gilbert Strang. Fourth edition. This is the required text in this course, and you need to purchase this one. And this is chapter 1 from this book. There are two main problems in linear algebra. One is how to find the solution of AX equals B, where the notation that we are going to use is all capital letters are matrices. So this is a matrix. It's an M by N matrix. M represents the number of rows and N represents the number of columns. Letters with an underline, letters that are underlined are actually, they are small letters, not capital letters. The underlined are vectors. Vectors are matrices with either one column or one row. If it has only one column, this is called a column vector. And if this is one row, this means it's a row vector. We can always transform a column vector or a row vector. We can always convert a column vector into a row vector by transposing, and I hope you know what that means. So AX equals B. The multiplication rules imply A is M by N. X has to be N by 1. So these are same. And then obviously B is going to be M by 1. Since this is the number of columns is 1 here, these are both are column vectors. So a matrix times a column vector is another column vector. And when we say okay, we want to solve this AX is equal to B, so solution of AX equals B simply implies find X that satisfies this equation. Okay, so this simply means so we'll do some examples and then we'll see okay, what does this mean. So A is known, B is known. So A and B are known. They are known, and X is the unknown over here. So this is what it means by when you say you need to find the solution of AX is equal to B, which simply means you need to find X. So this is the first one of the two problems of linear algebra that you need to solve this set of equations. The other problem in linear algebra is, which we'll do in the later half of the course, or probably most likely after the midterm. The other problem is this one. So the second problem in linear algebra, these are only two problems. So second problem in linear algebra, and this is after the midterm, hopefully inshallah, and probably on campus after the midterm. The other problem is ax equals lambda x. You need to solve ax is equal to lambda x. Lambda is a scalar. This is a vector. This is a vector. Again, these are column vectors. And this A is a matrix. When we are going to solve this one, we are going to assume A is a square matrix. A is a square matrix. We can always also solve this problem. So this is called so these x's are called, these column vectors, they have a special name. These are called the eigenvectors. These are called the eigenvectors, and this scalar is called the eigenvalue. So when you're solving this problem, what you're trying to do is, so A is n by n, this is n by n, n by 1, this is also n by 1, and this is a scalar. Scalar has no dimension, or if you want to say this is a 1 by 1 matrix. So when you're solving this problem, Ax is equal to lambda x, we are going to assume inherently that A is a square matrix. You can always also solve this problem when A is not square. So then this eigenvalue problem becomes a singular value decomposition. This becomes a singular value decomposition. It's exactly the same thing. The only difference is how do you compute these special eigenvectors. This is called the singular value decomposition. And this is the general case when A is rectangular. When A is rectangular, this means A can be a fat matrix. So this is a fat matrix. So this is 1, this is m, so number of rows. This is 1, this is n, number of columns. So obviously m is less than n. So number of rows is less than the number of columns. And the other case is, this is a tall matrix. This is a tall matrix. So 1 to m, 1 to n. So here m is greater than n, and obviously the number of rows is still m. Always number of columns is still n. So now you have the number of rows is more than the number of columns, and we'll see later on that the number of columns actually means, so maybe I write it here, number of columns is equal to the number of unknowns. So whether the number of unknowns is more or less than the number of equations, then how do we solve these problems? So this is the second half of the course where you actually don't want to solve this one. You want to actually diagonalize a matrix. So this is known as the diagonalization problem. It's known as the diagonalization problem, where you want to diagonalize, and we'll see why do you want to diagonalize a rectangular or a square matrix. So this is the later of the half of the course. In all I want to say here is, okay, you have only two problems to solve. Either ax is equal to b, or ax is equal to lambda x. So once you solve these problems, once you are able to solve these problems, once you know how to solve these problems, you should have a good grip on your linear algebra tools, or how do you deal with the matrices. Okay, so the first section deals with chapter 1 deals with how to solve linear equations. So how to solve linear equations. There are four methods. So there are four methods to solving linear equations. So let's start with two simultaneous equations. So let's take, so for all the cases we'll just use these equations. So we have 1x plus 2y equals 3, and we have 4x plus 5y equals 6. So before I do that, before I do that, let me plot this one. So how do we plot this one? So in 2D, in two dimensions, x and y, a straight line, a straight line, a straight line is represented by a straight line is represented by ax plus by plus c equals 0. So this is the equation of a straight line. Maybe you're not familiar with this one, so let me rewrite this one. So I can always rewrite this one as by equals minus ax minus c, or y equals minus a over b. Obviously b is not equal to 0, so if b is equal to 0, obviously we cannot divide, into ax plus minus c over b. And now if I say this is m and this is some c naught, then you know, okay, this m is the slope, and this is your familiar y is equal to mx plus c equation. Y is equal to mx plus c naught. So same here, no difference. I want to write the straight line equation like this because I'm going to extend it and make this a plane in 3D in a little while. Okay, so we have 1x plus 2y is equal to 3. So this I can write as, this is y is equal to minus half x plus 3 by 2, and this means y equals minus 4 by 5x plus 6 by 5. So if I multiply by 5, I get 5y. If I bring this 4x on this side, this is 4x plus 5y is equal to 6. If I multiply by this by 2, so I have 2y. I bring this on this side, so it's x plus 2y is equal to 3. So let me plot this one. So my equations are y equals minus half x plus 3 by 2. This means the slope is negative. Slope is negative. Okay. And the other equation is y equals minus 4 by 5x, again negative, plus 6 by 5. Okay. So these are the y-intercepts. So if I sketch this one, so when we say we need to find the solution of these two equations, when we say we want to find a solution of these two equations, this simply means we want to find where they intersect, right? So solution simply means solution of these equations imply where they intersect. Okay, so let's see. So x and y, this is y, this is x. So both are going to be like this. So this line, x is equal to 3 by 2 is 1.5 and 6 by 5 is 1.2, right? So maybe these will be like this. So this is slope is half. So slope is half means, so let me redraw it. So slope is half means it's like this. And when the slope is minus 4 by 5, this means this is like this, right? So this slope is 0.5, this slope is 0.8. So obviously the slope is more than this one. So this equation is y is equal to minus half x plus 3 by 2. This equation is y is equal to minus 4 by 5x plus 6 by 5. This is 0. Obviously, this intercept is going to be 3 by 2. This is 3 by 2. And this intercept is going to be 6 by 5. And obviously 6 by 5 is less than 3 by 2, so this is smaller. This is where they intersect. So this is our solution. This is our solution. And how do we find this solution? So there are 4 ways. The first one is by elimination. So first approach is, maybe I write 1. There are four methods. So first is by elimination, and this is credited to Gauss. So this is Gaussian elimination. So what you do is, how do you solve simultaneous equation? You say x plus 2y equals 3, and then you say 4x plus 5y equals 6. So x plus 2y is equal to 3 and 4x plus 5y is equal to 6. You multiply this equation by 4. So if I multiply this equation by 4, I'll get 4x plus 8y equals 12. And this one is as is. This is simply multiplied by 1. So multiply this one, the first one, by this coefficient, and multiply this one by this coefficient. So you'll have 4x plus 5y equals 6. Subtract both these. This will cancel. 8 minus 5y is 3y equals 6. This simply implies y is equal to 2. Substitute y is equal to 2. So obviously this point is 2. The solution is 2, comma, and obviously this has to be negative here, because if this is positive, we know this solution has to be negative. So if I substitute y is equal to 2 in either of these equations, so I'll get x equals 3 minus 2y, which is equal to 3 minus 2 into 2, which is equal to 3 minus 4, which is equal to minus 1. So my solution is minus 1, comma 2. So this is x. So this implies, or x equals minus 1. So these are my two solutions, minus 1 and 2, which from the graph appear to be correct. If you substitute x is equal to minus 1 and y is equal to 2, so minus 1 plus 4 is equal to 3. Minus 4 plus 10 is equal to 6. So both satisfy this equation, these two equations. So these are correct. So you can always substitute the values and see whether the solutions are correct or not. The second method is the Kramer's rule. Second method is the Kramer's rule. Since this is a 2 by 2 system, it's easier to solve. So for the Kramer's rule, what we are going to do is, I'll write this equation, and I hope you know this from your high school. X plus 2y equals 3 and 4x plus 5y equals 6 can be written in matrix form like this: 1, 2, 4, 5, x, y equals 3, 6. So this is our equation. So this is A, this is some vector x, this is some vector b. So a and b are known, and this x is unknown, and we need to find this x. Right? So I hope you know from your high school how to write this system of equations in matrix form. So Kramer rule simply means, if you want to find x, replace b by the first column here. If you want to find y, replace y by the column over here. So Kramer's rule simply means x equals, so you need to find determinants. So determinant of A. So determinant of A is 1, 2, 4, 5. 2 and 5 are the same here. Replace this column by, for x, replace this column by this b. So this becomes 3 and 6. So this becomes, so I hope you know how to find determinant. Determinants for 2 by 2 cases, you simply multiply the elements along the main diagonal, and then you subtract the elements along the off diagonal. So these are subtracted, these are subtracted, these are so the product along the off diagonal is subtracted from the product along the main diagonal. So 5 into 3 is 15. 15 minus 6 into 2 is 12, divided by 1 into 5 is 5, minus 4 into 2 is 8. So this is 15 minus 12 is 3. 5 minus 8 is minus 3. So this is minus 1. So x is equal to minus 1. X is equal to minus 1. For y, and for y, same thing here. The denominator is the same. 1, 4, 2, 5. And instead of the first column, since y is the second variable here, instead of the first column, replace the second column by b. So we'll have 1, 4, and 3 and 6 over here. So again, main diagonal is 6 minus off diagonal is 12 divided by denominator is still the same, my 5 minus 8. So this is minus 6 over minus 3, which is equal to 2, which is exactly the same. So this simply means you have minus 1 comma 2. The solution is still the same. Okay. The third approach is the row echelon normal form. The third approach is the row echelon normal form, or it is also called the reduced row echelon form. Row echelon normal form. And what we do over here is we again try to do elimination by performing. So you perform row operations. And these are elementary row operations. So perform elementary row operations. Perform elementary row operations. So if we want to perform elementary row operations, so again, if you look at the matrix, so x plus 2y equals 3, 4x plus 5y equals 6. So I can write this one again as 1, 4, 2, 5, x, y equals 3, 6. So let's write this combined system as like this. So 1, 4, 2, 5. This separator simply means this is A and this is B. This is 3, 6. What we want to do here is we want to get rid of this 4. So how to make this 0. So how to make this 0? So if I do, so please be careful when you write this operation. So the correct notation is this one. If I multiply 4 times the first row and subtract it from the second row, this will go to 0. And this is actually what I did here. If I multiply the first row by 4 and then I subtract it, then I get I can get y there. So what I'm going to do is I'm going to write minus 4 times r1 plus r2. So this is row 1. This is row 2. And the row that you need to change should be written afterwards. So row 2 is the one that needs to be changed, and is the second one. And is the second one when you write this equation. So minus 4 row 1 plus row 2 is not equal to row 2 minus 4 row 1. Because here you are changing row 1. Here you are changing row 1. So since you want to change row 2, so row 2 should be written afterwards. So this becomes, so when we do this operation, the first row is not going to be changed. This is not going to be changed. So this is 1, 2, 3. So minus 4 into 1 plus 4 is 0. Minus 4 into 2, which is 8, plus 5 is, so 8 minus 5 is 3. Minus 4 into 3 is 12. Minus 12 plus 6 is minus 6. Right? I can stop here. I can stop here and I can solve this equation, this system. This system is exactly the same as this one. All we have done is whatever operations we have done on this side, we have done the same operations on this side. So the equality still holds. This equality still holds. This is not going to work. This is not violated. So if I want to solve this equation here, I can write this one as the first equation is the same. So this is x plus 2y equals 3. And the second equation is 3y equals minus 6, which gives me y is equal to minus 2. But this is not the row reduced echelon form or the row echelon normals form. So for what we want to do next is I want to get rid of this 2. How do I get rid of this 2? To get rid of this 2, I can, and I want a 1 over here. I want a 1 over here, and I want to get rid of this 2. So what I do is I can do either, I can perform either operation, either get rid of this 2 first or I get rid of this 3 first, but I want to change this 3 to a 1 first. So what will I do is I will say row 2 divided by 3. So row 2 divided by 3, I'm sorry, this is I think minus 3. So this is minus 8 plus 5. So this is minus 8 plus 5, so this is minus 3. So this is minus 3, y is equal to minus 6, or this means y is equal to, which is the same as before. So, but I'm going to reduce it further or simplify it further. So when I do row times row 2 divided by 3, this simply means this equation is simply divided by minus 3. I'm sorry, this should be divided by minus 3. So if I divide this equation by minus 3, so this will become 1, 0, this will become 1, this will become 2. So I'll get the first row remains unchanged. So this is 1, 2, and 3. And this is 0, 1, and 2. Now what I want to do is I want to change this 2 to a 0. So I say minus 2 row 2. And since I want to change row 1, I'll say minus 2 row 2 plus row 1. So because of this 0, this is not going to change. This is not going to change. This will be changed. So since I am changing row 1, so I'm changing row 1. So this what will happen is I'll get 0, 1, and 2 over here, 1 over here. Minus 2 plus 2 is 0. Minus 4 plus 3 is minus 1. And this system of equation is nothing more than saying, okay, this x equals minus 1, because x and y are, this is an identity matrix. This is an identity matrix. So I times x, y equals minus 1 and 2. So all I'm going to say is x is equal to minus 1 and y is equal to 2, which is exactly the same as the solution that we got in the first two cases. This, by the way, is called the non-singular case. This is the non-singular case. And if you recall, non-singular case will give you one unique solution, implies a unique solution. And singular or non-singular is only related to square matrices, a unique solution. So a unique solution, non-singular means, so let me write it here. Non-singular simply means your determinant. So this is how you write the determinant. So determinant of A is not equal to 0. So obviously determinants are only calculated for square matrices. So it doesn't make sense to say a rectangular matrix is singular or non-singular. It's only square matrices are singular or non-singular. So that if the determinant is not equal to 0, you'll have a unique solution. And probably if you recall, maybe you have seen this before. So if you have this matrix A, B, C, D, you say you have a unique solution. You have a unique solution if AD minus BC is not equal to 0. This is what this says. Your determinant is, this is what it says. So this is, by the way, the determinant of A. So when the determinant of A is not equal to 0, you say the matrix is singular. Okay. So just remember the notation here. The row that is written later on is the one that is to be changed, not the first one. So again, this is not the same, although mathematically you will say this is the same, but here you are changing row 2, here you are changing row 2, here you are changing row 1, according to the notation in this book, and which is generally followed. So kindly remember, whatever the row you want to change, that should be written later on. Okay. Since we have done the non-singular case, let me look at the singular case here too. So what is the singular case? So in the singular case, either I have no solution, And when do I have no solution? I'll have no solution. This implies lines are parallel. Lines are parallel. So when will these lines be parallel? So if we go back to our picture, over here, so if these lines, if there is a line which is parallel to this line, obviously they are not going to intersect. If they're not going to intersect, so this means the slope is going to be the same, the slope is going to be the same, the offset is going to be different, because if the offset is different, then the lines will be parallel. So if you recall that picture, and then we go back to the singular case. So no solution implies lines are parallel. So for example, if you have x plus 2y equals 3, if I simply multiply this one by 4, I'll have 4x plus 8y, and then I say that this is not equal to 3, I say this is not equal to 12, I say this is equal to 6. If I say this is equal to 6, so here the slope is minus half. What is the slope here? The slope here is also minus half, minus 4 over 8, which is minus half. So the slopes are the same, but the intercepts are different. So these lines are parallel. So whenever the right-hand side, when you multiply the left-hand side by a certain number, and the right-hand side doesn't give you the same number, then you say the lines are parallel. This will have no solution. Because if you eliminate, so after elimination, you will get 4x plus 8y equals 12, 4x plus 8y equals 6. If you subtract, so this will cancel. So this is 0 is equal to plus 6. So obviously 0 cannot be equal to plus 6. So that's why we say that this implies no solution. Okay. The second case over here is you have infinitely many solutions. Infinitely many solutions. And how do you get infinitely many solutions? If the two lines are on top of each other. So lines are on top of each other, because they are intersecting at infinitely many points, then are on top of each other. So when the lines are on top of each other, this simply means, for example, x plus 2y equals 3, and then I say 4x plus 8y equals 12. If I do this, and if I do the elimination, so elimination gives 0 equals 0, because here now slope is same, slope is minus 1 over 2. Here slope is still the same, slope is minus 4 over 8, which is minus 1 over 2. The intercept here is 3 over 2. The intercept here is 12 over 4. 12 over 8, I'm sorry. 12 over 8, which is still 3 over 2. So since Since the lines are exactly on top of each other, you have infinitely many solutions. So these are the two cases in two-dimensional that gives you infinitely many solutions. Okay, so let's go back to our fourth case. So fourth and the last approach is matrix inversion, which is never advised. So you should never do matrix inversion because you don't know whether the inverse will exist or not. And if the matrix is ill-conditioned, then you have another problem. So again, our equation is x plus 2y equals 3, 4x plus 6y, sorry, 4x plus 5y, 4x plus 5y equals 6. So this means 1, 2, 4, 5, x, y equals 3, 6. Okay. So this is A, this is X, this is B. Since determinant of A is not equal to 0, this implies A inverse exists. And what is the A inverse for a 2 by 2 matrix? So which implies A inverse is simply 1 over the determinant of A, because if the determinant of A was 0, you cannot divide this thing. And then for a 2 by 2 case, you swap these two. So this will become 5, this will become 1, and you subtract, negate these two values. So this will be -2, this will be -4. So since the determinant of A we found was 5 minus 8, which is -3. So A inverse is -1 over 3 over 5 -2 -4 and 1. Why? Because determinant of A is simply 5 minus 8, which is -3. Okay. Now, the only thing that you need to be careful with matrix equations is if this is AX is equal to B, I cannot multiply an inverse here because this is an n. This is an n by 1 thing. I cannot multiply a vector by a matrix. I can multiply a matrix and a vector, but vector cannot multiply a matrix. So I'll put an A inverse here. If I put an A inverse here, so this is wrong. So if I put an A inverse here, so obviously I'll put an A inverse here. I cannot put an A inverse here. If I put A inverse on the left of A, I'll put A inverse on the left of B. Okay, so I know this is going to be identity. You can after the lecture, you can always check whether the A inverse is identity or not. So this means X is simply A inverse B. So let's find this one. So A inverse is -5 over 3 plus 2 over 3, 4 over 3 minus 1 over 3 multiplied by B. B is 3 and 6. B is 3 and 6. I hope you know how to multiply. So you will, there are three ways of multiplying a matrix and a vector or two. So we'll see. So the easiest one or the one that you already know is you take this row and you multiply by this vector. So this one here, this gives you the first element. So the first element is going to be -5 over 3 into 3 is -5, -5 plus 2 over 3 into 6 is 2, 4 plus 4, which is equal to -1. And obviously this is X and Y. This is X, this is Y. And this will be, for the second element, this is 4 over 3 into 3 is 4. And this is -1 over 3 into 6 is -2. So this is 2. So X and Y are -1 and 2 again, which is exactly the same as before. So in this chapter, we are going to focus on, so in this chapter, our focus will be on, our focus will be on the elimination method, on the elimination method, on the elimination method, and we want to convert everything into the row reduced echelon form. Okay. So let's look at the geometry of linear equations. So geometry of linear equations. So again, so when I say geometry of linear equations, we can actually look at it two ways. Either we can look at the row picture or we can look at the column picture. So let's look at an example. So we have 2x minus y equals 1, and I have x plus y equals 5. Okay. So row picture simply means, row picture simply means I look at one equation at a time. So look at one equation at a time. One equation at a time. And then find their intersection. Okay, so if I plot this one, so this is y, this is x. So 2x minus y equals 1. In our familiar notation, we get y equals 2x plus 1. So the slope is 2, and this implies y equals minus x plus 5. So here the slope is negative. So slope is negative here, the slope is positive here. So positive slope means I'm going to, and then when x is equal to 0, y is equal to 1, or I'm sorry, this becomes minus 1. When this goes on this side, when this goes on this side, it becomes a minus 1. So when x is equal to 0, y is equal to minus 1, so positive slope goes like this. So this point is minus 1. This equation is y is equal to 2x minus 1, or maybe I write it in that form. This equation is 2x minus y equals 1. And then this is a negative equation. So when y is equal to x, when x is equal to 0, y is equal to plus 5. So this goes like this. So this is plus 5. This equation is x plus y equals 5. So obviously this is the point of intersection, and this point of intersection is we can always find out. So what is the point of intersection? If I multiply this one by 2, I will get y equals minus 2x plus 10. This one is y is equal to 2x minus 1. If I add these two simply, so I'll get 2y equals I'm sorry, this is y is equal to 2x minus 1, and this is so this is 2y, I'm sorry. When I multiply this one by 2, so this will become 2y. So 2y, so this will become 3y. 3y is equal to 9, or this implies y is equal to 3. So if I put y is equal to 3 in this equation, so I'll get 3 plus 1, 4, so x is equal to 2. This implies x is equal to 2. So this is 2 and 3. Maybe it's not drawn according to scale, but this is what distribution is, 2, 3. Okay, so this is the row picture where you look at each individual equation and plot it and find the point of intersection. Okay. So you need to find the point of intersection. What about the column picture? What about the column picture? So column picture, what you want to do is I can always write this one as a vector plus this one as a vector equal to this one as a vector. So this is simply vector addition and scalar multiplication. So let me write this equation again. So 2x minus y equals 1, and then I have x plus y equals 5. Okay, so I can always write this one as 2x outside. I can write this as x outside, 2 and 1 here, plus y outside, minus 1 and plus 1 here, and this is simply equal to 1 and 5. So these are scalars. These are scalars. And these are vectors. So in a column picture, what we are doing is we are doing vector addition, vector addition, vector addition, and scalar multiplication, and scalar multiplication. Okay, good. How can we represent vectors? So we can represent vectors. So we can represent vectors as column vectors, or we can represent vectors as a list. So this can be alpha beta. This can be alpha comma beta, or so this is the first way. This is the second way, or this one we can represent them as a vector from the origin. So in two-dimensional, because these are two-dimensional. So this is some vector. So this is alpha over here, and this is beta over here. So we can represent vectors as column vectors. We can represent vectors as lists, or we can represent vectors as an arrow from the origin, by arrow from the. So we are going to use this notation. So if this is this notation, let me write this one. So this becomes straight line actually. Is the vector 2, we already know the solution. We already know x is equal to 2, x is equal to 2, and y is equal to 3. So we know this solution. So we know x is 2 times, y is 3 times. So if x is equal to 2 times, so 2 into 2 is 4, minus 3 is 1. Whenever you multiply a scalar by a matrix or a vector, you multiply every element of the matrix by that scalar. So 2 times 2, 1 is simply 4 and 2 over here. 3 times minus 1 and plus 1 is simply minus 3 and plus 3. So minus 3 plus 4 is 1. Plus 3 plus 2 is plus 5. So these are all right. So all I'm going to do is I'm going to draw these vectors, and then I'm going to do I'm going to scale them. So 2 and 1 simply means 1, 2, 1, 2. So maybe this is not 2, 1, 2. So this is 2, x is 2, y is 1. So this vector is like this, right? So this is 2, and this is 1. And then this vector is minus 1 and plus 1. So minus 1 here, plus 1 here. So this vector is minus 1 and plus 1. Okay. So this is x-axis, this is y-axis. Now, 2 times a vector is simply, I simply extend it. So this becomes 3, this becomes 4. So this comes over here. So this vector is 4, 2. So I'm using this notation now, the list notation. So 4, 2 is this vector, and this is 3 times this one. So this will go to minus 1, minus 2, minus 3 here, and plus 3 here. So this goes over here. Again, this is simply scaled over here. So let me just scale this one to minus 3. So this is minus 3 plus 3. Okay. And how do I get this point? And how do I get the resultant? So this is simply the parallelogram rule of adding vectors. So when I do the parallelogram rule of adding vectors, so when I add 4, 2, so when I add 4, 2, and I get plus minus 3, 3, minus 3, 3, this should be equal to 4 minus 3 is 1, 3, 2 is 5. So I should get some 1 here, 4 here, 5 here, so somewhere over here. So I should get uh, this resultant. Get rid of this one. No need of this one. And then this is so this is same as, so in this vector, what I've done is, in this vector, I have added this vector. When I add this vector, so this is minus 3 and 3. So when I add this vector, this will become 1 and 5. So this vector is 1, 5, which is our resultant vector. And when I connect this one to this one, this is my parallelogram or head to tail rules of adding vectors, right? And this is your 1, 5. This is your 1, 5. This is your B vector. Okay? So this is how you add, look at the column picture, which is like, so this right hand side, so this vector B is simply combination of columns of A. And this is as a fancy name. In chapter 2, we'll say this is simply the column space. So if B lies in the column space of A, then we say we have a solution. If B does not lie in the column space of A, then we do not have a solution. Okay. What happens in 3D? So in 3D, we have this plane. So in 3D, we have this plane, and this plane is simply, let's look at an example. So 2u plus 1v plus 1w equals 5. 4u minus 6v, there is no w here, equals minus 2. And then I have minus 2u plus 7v plus 2w equals 9. So in 3D, equation of a plane with zero thickness. So a plane is one which has no thickness. So no thickness. So a plane is described by ax plus by plus cz plus d equals 0. So compared to the line, you have this z dimension over there. Otherwise, it's exactly the same as that line. Okay. Again, so if I look at this equation, so how do I plot this one? So how do I plot this one? So it's very simple. So what we do is we say so u, v, w, this is the origin. If this 5 is a 0, this implies plane passes through the origin. Plane passes through the origin. And why is that? Plane passes through the origin. So if this is 0, plane passes through the origin. Why? Because if I make v and w means u and u is 0. If I make u and w 0, this means v is 0. If I make u and v 0, then u and v is 0, then this means w is 0. So if the right hand side is 0, this means the plane passes through the origin. If this is not 0, this means the plane does not pass through the origin. So to plot a plane, all you need to do is need 3 points. So if v and w are 0, u is 5 by 2. If u and w are 0, v is 5. and if u and v are 0, then w is 5. So this means either you have 1, 2, 2.5 here. So this is 5 by 2. This you have 1, 2, 3, 4, 5. You have 5 over here. And then you have 1, 2, 3, 4, 5. You have 5 over here. So this triangle, this triangle is in the plane. This triangle is in the plane, right? So all I can do, what I can do is I can say, I can simply extend this one. So I can draw this thing here. I can draw this thing here. And then I say, this is my plane. This is a sloping plane, right? This is a sloping plane because my triangle is like, so the triangle, so for the plane, you only need 3 points, or you need a point in 2 lines to draw a plane. So this plane contains this triangle. Okay, good. Okay. What about the second equation? So whenever 2 planes intersect, if they intersect, that will be a line. So when they intersect, it will be a line. So when the planes intersect, this will be a line. So look at this plane now. So this plane, so this is actually a line in 2D, in 3D, 4u minus 6v is equal to minus 2. So this means if v is equal to 0, u is equal to minus 2 by 4, which is minus half. So if I extend this one, so u is somewhere over here. So this is minus half. And when I say u is equal to 0, v is equal to plus 1 over 3, 2 over 6. So v is somewhere on this line. So this plane, this line is actually like something like this. So this is the line. This is in the UV plane. This is not in the UV plane. This is not along the W axis. This is in the UV plane. So if I draw another, so if I draw a plane which is, so for all values of W, because this line is in the UV plane. This line is in this plane. If this line is in this plane, then it can take on any value of W. So if I draw another plane which contains this line like this, with same slope, same direction, like this probably. Yeah, should be all right. So these are the 2 planes, and they intersect at this point, and they intersect at this point. So this is actually should be a line. There's not a straight line. This is some line. So this is the line of intersection. Right? So let me say this one is 2u plus v plus w equals 5. If this 5 becomes a 0, this plane passes through the origin over here. This is independent of w. This is independent of w. No need to sketch it in the negative w axis because the other plane is in the positive axis. So independent of w, and this line is 4u minus 6v equals minus 2. So the third plane, if there is going to be an intersection, the third plane is going to be going inside this board, and this would be some point over here. So if there is an intersection, and we'll see that this point is actually 1, 1, 2. This is the point of intersection. This is the point of intersection with the third plane. If there is some intersection, if there is no intersection, then obviously we won't have a solution. Okay. Okay. So, and you should also say, so this is the line of intersection. This is the line of intersection of first 2 planes, of first two planes. This is the line of intersection of first two planes. In 3D, in three dimensionals, uh, a line requires two equations. A line requires two equations. A line requires two equations, which we have just plotted. But in n dimensions, it requires n minus 1 equations. Okay. Okay. Let's look at the column picture. So this is the row picture. So this is the row picture where we have looked at each individual equations. What about the column picture? So column picture, again, do the same thing. Look at the columns. So the columns are, so if I write the equation again, so 2u plus v plus w equals 5, 4u minus 6v equals minus 2, and then I have minus 2u plus 7v plus 2w equals 9. Okay, so this I can write as u 2, 4 minus 2 plus v 1 minus 6 plus 7 plus w, which is 1, 0, 2. This is equal to b, and this where my b is 5 minus 2, 9. So again, if b lies in a combination in a space generated by this combination of vectors, we say we have a solution. Otherwise, we will not have a solution. And we know, or we'll know in a little while, okay, u should be 1, v should be 1, and w is 2. So if this is the case, then you can see 2 plus 1, 3 plus 2 is 5. 4 minus 6 is minus 2, plus 0 is minus 2. Minus 2 plus 7 is plus 5, plus 4 is 9. Right? So these solutions are all right. So obviously B lies in the column space generated by this one. So how do we look at the column picture? So to look at the column picture, let's draw this vector first. 5 minus 2, 9. So the 5 minus 2, 9 is going to be like this. So this is X, this is Y, this is Z. So this is actually 5, 0, 0 plus 0 minus 2, 0 plus 0, 0, 9. So when you add the vectors, so 5 plus 0 is 5, 0 minus 2 plus 0 is minus 2, 0 plus 9 is plus 9. So 0, 0, 9 is over here. This is 0, 0, 9. This is 0, 0, 9. 0 minus 2 is somewhere over here. So this is 0 minus 2, 0. So this is 0 minus 2, 0. This is 0, 0, 0. And then we have 5, 0, 0. So somewhere over here is maybe less here, not so maybe here. This is 5, 0, 0. So if I do a head-to-tail rule over here, this is my resultant over here. This is a resultant here. If I add this 0, 0, 9 over here, this vector over here, so this is my resultant vector. This is my resultant vector, which is 5, -2, and 9. Right? Okay. And if I look at the column picture, which probably I'm not going to draw because I'm not good at drawing this one, maybe I'll mess it up, but I'll just give you an idea. If you know MATLAB, probably that's the best tool to plot this one. So this is X, this is the origin, this is Y, this is Z. So we want, what we want is, look at this vector. If you look at this vector, this is 1, 0, 2. So 1, 0, 2 means 1 here, 0 here, and 2 over here. So 1 here, 2 here, maybe one over here. So 1, 0, 2 simply means I have a vector like this. Again, this vector is in the xz plane. This is in the xz plane. This is an xz plane because y is equal to 0. And then if I, so 1, 2, so if I extend this one, this will be 2, 0, 4. So this is 2, 2, 0, 4. This is one vector. And then there is another vector. There is another vector which is, if I add these two, if I add these two, I'll get 2 plus 1 is 3, 4 minus 6 is -2, and -2 plus 7 is 5. So if I draw this vector, 3 minus 2, 5, this vector is somewhere over here, this one, and then I add this one over here. I mean, I add this one over here. This is this one parallel to this one. I have to make this one, then I'll redraw this one. So this is parallel to this one, and this one is parallel here. Probably makes sense. So this one is same as this one is same as this one. So this is my resultant. This is my resultant, and this resultant is still B, 5 minus 2, 9. So obviously this is not drawn as well as I should have, or as well as the software would have done it, but should be all right. Okay. Let's look at the singular case, and then we'll stop. Stop for today. So in the singular case, again, this is the non-singular case. This is the non-singular case where we have a solution, implies unique solution. Unique solution. So singular case in 3D. Singular case in 3D we can have, so now we are looking from the top. If you are looking from the top, so maybe we have some situation like this. We have where we have two planes that are parallel. So two planes are parallel. Two planes are parallel. You're looking from the top. Or we have planes that intersect. So when we have planes, so you're looking from the top. So look from top. So look from top. So here we have three planes. So there are two planes are intersecting at a time. So pair of planes intersect. Pair of planes intersect in a line that is in lines that are parallel. Pair of planes intersect in a line that are parallel. In lines, not in a line, in lines that are parallel. And these are the parallel lines. If you look inside into the paper, so there is a line here, there's a common line here, there's a common line here, and all of these are parallel. Or the other one is you have two planes that intersect, and then there is another plane that intersects like this. So you have an infinitely many possible solutions. So infinitely uh, many solutions, infinitely many solutions. Here there is a line of intersection. There is a line of intersection, just like uh, uh, when two lines in 2D, when there are two lines that are have the same slope, same offset, and on top of each other, you have an infinitely many solutions. That is exactly the same case here. And the last one is you have three planes that are parallel. So three planes that are parallel. So this is the most, these two are the most common cases. These two are the most common cases. And let me tell you, let's look at this example here. Again, same example. So if I look at the same example, or maybe another example, u plus v plus w equals to 2u plus 3w equals 5. And then I have 3u plus v plus 4w equals 6. Now if I add these two equations, I'll get the third one. So if I subtract this third equation from the first two equations, I will get 0 equals 1. 0 equals 1 after elimination. After elimination, this is what I get. 0 is equal to 1. So obviously it's an inconsistent. So this is inconsistent system. So it's an inconsistent system. What happens if I change this 6? If I change this 6 to a 7? If I change this 6 to a 7, this implies I have 0 is equal to 0, which is what I get over here. Where all the lines, now you have an intersection. We have too many solutions. So if this is a 7, this implies you have too many solutions. Okay. And before we end, let me give you some example, one definition. Three vectors are coplanar, that is the line in a plane. So in 3D, this is in 3D. Three vectors are coplanar if they are linearly dependent. If they are linearly dependent. And whenever you have three vectors that are coplanar, you can always draw a plane that are linearly dependent. And what is the definition of linearly independent? Linearly dependent. So linearly dependent implies if you have scalar C1 column A1 plus C2 A2 plus Cn An. This is equal to the 0 vector. So these are scalars. Obviously, A's are vectors. These are vectors. This is a vector. This is a 0 vector. So if Ci is equal to 0 for all I is the only solution, then AIs are independent. If this is not the case, then they are dependent. Then AIs are independent vectors. If this is not the case, then they are dependent vectors. And we can see 3 times 1, 2, 3 plus minus 1 times 1, 0, 1 plus this from here. 1, 2, 3, 1, 0, 1, and 1, 3, 1. And 1, 3, 4. This is equal to the 0 vector. Since these are not equal to 0, so we can say 3 minus 1, 2, 2 minus 2 is 0, 6 plus 0, minus 6 is equal to 0, 9 minus 1, 8, minus 8 is equal to 0. So this is C1, this is C2, this is C3. Since C1, C2, C3 is not, so since C1 is not equal to 0, is C2 is not equal to 0, or C3 is not equal to 0, this implies vectors are dependent. Vectors are dependent and they define a plane. Vectors are dependent. Okay. And the last thing, if n planes have no point in common or infinitely many, if n planes, the singular case, if n planes have no point in common, or infinitely many, then n columns lie in same plane. Simply means they are coplanar, implies coplanar. Or for our case, or for a B which is 257 will have, or a B which is this one will have infinitely many solutions. Infinitely many solutions. So let's stop the lecture here today, and we will start from the Gaussian elimination section in the next lecture. Okay. If you have any questions, you can always send me your questions via email, or we can discuss them in the next lecture. Thank you.